Okay, hello everyone, welcome back to the channel. My name is Mtanda Samil. Okay, it has been quite long, but this time around we are back with item 5 of our Jjeb, which you can call ginger joint moko examinations board. Okay, good, we are in for item 5. All right, we are in for item 5 without wasting time. And please, just like the other items we have been having, it is very enticing, very enticing. In fact, it is very enticing beyond measure, so better watch it to the end such that you don't miss out. Okay, good. Now, okay, without wasting time, I think let's get there. But before, please, you are reminded to subscribe to the channel. Yeah, you are reminded to subscribe to the channel such that you don't miss out the forthcoming videos. In fact, you never know that this will be even the last video. Yeah, why I do that, or why I keep on postponing about limiting the channel to only my subscribers, is that people always come into my inbox telling, okay, well, they claim they don't know how to subscribe, so I tend to always give some time, but I think it's even out. So better subscribe right away after watching this video. Make sure you can subscribe so that you don't miss out the other forthcoming videos, of course hot ones, still from Jjeb. All right, let's now proceed. Yeah, of course, when you subscribe, you'll always be notified on when we have posted a video. Okay, so we now going to have item 5 done. Okay, once again, I've said it's very enticing, and it has very many learning points to both a teacher and a learner, most especially those who are going to sit for their forthcoming exams. Okay, all right, good. Let's look into this slowly. We get it answered and we call it a day. So, due to weather changes, of course, item 5, due to weather changes, your region has been struck by heat waves resulting into scarcity of water for farming and too much heat inside houses. Oh, that's really bad. A meteorological team from the Ministry of Disaster and Preparedness informs the population that the time to cultivate land for crop farming is when the atmospheric pressure is below 740 millimeters of mercury. Please, this one's read as millimeters of mercury. Reason, in chemistry, Hg is the symbol for mercury. Okay. The government has advised your region to make kettles and pots using clay. Oh, do you think it's just easy like that? Anyway, and use them with metal sheets to address the issue of clean water for drinking. Anyway, shall be looking into that. How can that be done? Shall be seeing that. Okay. Hang moist sisal or banana fiber curtains on the inside walls to reduce heat inside the houses. Anyway, in this generation where we have, okay, okay, I know I guess the someone doesn't even know what banana fiber is, or to only the few ones who grew up in the village can at least tell. However, don't worry, in this video I have the picture for you such that you will be able to know what a banana fiber is, especially, and I don't want to use an abusive language here. Okay, houses, and also build high water tanks out of repurposed plastic containers locally made to act as water reservoirs. Okay, so they need to have somewhere they will be storing their water from for future use. The population has been advised to extract groundwater using handpumps. Oh, that is really cool. A bit cool. To raise the water into the tank so as to bring water to residences, making sure that there is sufficient pressure at the taps for irrigation and household use. However, this water is not clean for drinking. Anyway, sorry for that. Oh, sorry. If the water is not clean for drinking, then it's not good. Hint, they're saying the amount of heat required to vaporize 2 kilograms of water from drinking it's meant to be for drinking at, let's get this harmonized. Okay, so we have harmonized it already. So they're saying to vaporize 2 kilograms of water for drinking at 60 degrees Celsius is 4.55 exponent. Okay, I think still again, let's look. Okay, we proceed. So okay, we get our laser pen. So they're saying the amount of heat required to vaporize 2 grams of water for drinking at 60 degrees is 4.55 times 10 power negative power 6. Okay, it is read as 4.55 exponent 6 joules. That's the amount of heat. Okay, specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Okay, the total pressure sufficient for the taps and irrigation is 15 kilopascals. This is kilopascals. K is kilopascals. Pascals is the unit for pressure. I guess you have already covered that task. But they're saying, let's make analysis. They're saying task. As a student of physics, carry out a scientific investigation to help the region establish if they can cultivate land for farming. Now, we need to look into that. Then, okay, let's go on by one. Let's go on by one. So, carry out a scientific investigation to help the region establish if they can cultivate land for farming. Let's go and look into that in part A. Let's go and see which can they even carry or establish okay the land for farming. So we have this point here which says a meteorological team from the Ministry of Disaster and Preparedness informs the general population that the time to cultivate land for crop farming, you see that, is when the atmospheric pressure is below 740 millimeters of mercury. Now, the word is atmospheric pressure. Must be this. Then, of course, ask yourself, how can we measure atmospheric pressure? We can measure atmospheric pressure using what we call a barometer. We can use a barometer to measure atmospheric pressure. Now, but of course, these are local people. Do you think they'll be able to buy a real barometer? Not really. But they can make a local one. They can make a local barometer. And that's what we have in part A. Let's go and see how we can make a local barometer. Okay. In part A, we want to see how we can make a local barometer in simple terms. Now, it all begins with here. To make a local barometer, I'll describe here like this. First of all, you will need, okay, a glass tube like that with an open end. Now what you will do, you will have to, in fact, pour here some mercury, like right there, mercury. Then you must put your hand to cover on the open end of the mercury. Then later on you do what? You will shake. Why do we shake? We shake to remove any air which is inside there. We shake to remove any air which is inside there. Then what you will do, you will get now another trough. A trough. You come and now invert this. This is just a simple description. Okay. You now get this glass tube of yours containing mercury, and you've already finished to shake it to drive away air. What you do now, pour some mercury into that trough or container. Then you would come and invert. Or you put the open end to be inside the mercury into the trough like that. You find that the mercury will find its way up this side like that. Now what you will do here, you will get a ruler and measure the mercury length in the glass tube. A mercury length L. Now that length is how much? If the length maybe is 740 centimeters, then you say they can now plant their crops, because high temperatures don't favor crop growing, by the way. So it should be that. It should be either that. In fact, if the length is 740, then that can suit the 740 millimeters of mercury. Let's go and look at that in details right here. We have a diagram here. I've tried to improvise one here which will work for us. Let's get started. Okay. So now we are saying that the materials needed, all you need is alright, the materials needed, we need a glass tube, we need mercury, we need a bowel, we need a meter roll, like that. Let's get our diagram ready. We look at this in details. Okay. So we are getting this drawn straight away without wasting time. Okay, let's get the drawing such that we can now explain this. We need a meter roll, glass bowel. Right, great. So let's draw quickly. All right, so all right, now so you realize that the glass tube is this one right here. That is our glass tube right there, if you're really keen about that. This one here is the mercury is what you're trying to bring here as those dots you're seeing in there. The bowel is like this one here. The meter rule, we didn't put it forward, but you all know how a meter rule looks like. You all know how meter rule looks like. So we're getting our diagram ready. Okay, let's get there. Then as our diagram is coming, please we remind you to subscribe, because on another video you won't be able to access this channel. Yeah, we are just going to limit it to only our subscribers. And of course, in the next video, please, I thank everyone who takes time to give a comment. And of course, anyway, I only forgot to put the screenshots here, but there is a, I don't know, I'm just forgetting, is it? Let me just try to read out these names here. Maybe there can be something sensible. As our diagram is coming, I'll be reading this for you. So these people comment a lot, and they are really good people. In fact, they impress me a lot. Just have their names. I don't know if I can remember them. Okay. So as you're getting our diagram ready, let's look into these people's names. Okay, there's one called the Jjeb Pro. Please, anyway, I don't know whether you're a student, but if you're a student, then I just pray you really make it in your final exams. In simple terms, wishing you success. Okay, then also there's another one. There is another one. I don't know whether I can be able to cite out this. Okay, then I think in the next video I'll be putting them forward. The one I can remember right now is called the Jjeb Pro. Then also there is one called the, okay, there's one called the Authentic. Then the other name is really challenging to me. Is it Range? I don't know. Authentic, yeah, I don't know now, I can't read this name, but one is called Authentic. Please, those are my outstanding subscribers who really come in to comment every time. Anyway, our diagram is ready. Let's now get into it. So realize that what you're having here is, this is here is the okay, this one here. Okay, let's go into this. All right, so let's proceed. You realize that now this is the diagram we have. This is how much we're in here. Now what you must know is that this one here is the atmospheric pressure. You can see this arrow here. This one here is the atmospheric pressure. Now atmospheric pressure, you can't really feel it, but just know there is natural pressure, which is always compressing liquids downwards to the bottom surface. So this compression force, which compresses the mercury downwards, is what we call the atmospheric pressure. Please, it exists everywhere, even where you are right now, where you're watching this video from. There is atmospheric pressure, but you can't really feel it. However, it is a very dangerous pressure, by the way. Okay, now, so as the atmospheric pressure is pushing downwards, you find that the mercury will be forced to move upwards. Now, the atmospheric pressure varies from place to place. Okay, you realize that when you go to raised areas, there'll be a different, like say, this is our mountain. There's a different pressure up here, and there's a different one down, like that. So now remember, our farmers were told that they can only work out this if they have 7 centimeters, okay, of mercury, 740. So now what you do, you come and just make locally, get a glass tube, yeah, a glass tube. You can just get a glass tube. Then what you do, with an open end, of course, then you will, okay, I explained that originally, I'll not repeat myself, but then the mercury rises up like this. Then what you do next is that you must come and put in the, now, are you seeing the level of the mercury level up in the glass tube? Yes. Now we need the height or the length L. Those blue arrows you're seeing here are showing us the length L. Now when you measure that length and realize maybe the length is 740, then you shall confirm these people to cultivate. But if it is above 40, remember, high atmospheric pressure does not favor crop growth. Better know that. So it should be 740 and below, maybe. That can really be a bit okay. So with that, let's go and get a description. So in simple terms, how do we come about this? But that's how we label, and that's how we get that done. Now let's go and see the description. So now we're saying that okay, we are now saying that a thick-walled glass tube, closed at one end, is filled with mercury and inverted several times with a finger, I explained that, covering its open end. Now, why do we do that? Okay, this is to remove air bubbles in the mercury. Yeah, of course I have to remove air bubbles such that here, okay, what I didn't read for you here was that, let's go back there. This one is called the torricellian vacuum, the torricellian vacuum, this one here. The small space which is remaining here, the space which remains in a tube, when the tube is containing mercury, call it a torricellian vacuum. A torricellian vacuum, that's what we mean by that. Now a vacuum is a place without air, so that's why we cover the open end such that we can get this covered right away. Okay, so this is to remove air bubbles in the mercury. Good. The tube is then completely filled with mercury, and with the finger still covering its open end, the tube is gently inverted into a bowl containing mercury. So maybe have our bowels there. So now inverting means the open end should face downwards. That's what I mean by inverting. Okay, the finger is then removed from the open end and the mercury is left to settle. Yeah, you leave it to settle. Okay, the length L of the mercury column is in the glass tube above the surface of mercury in the bowel is measured using a meter rule and recorded. So what we are doing here is that simply we are coming to measure this. Okay, we are measuring this length L, which is in simple terms the length from here up to the surface right there. That length there, the value we get is what we shall, okay, consider or take forward. Okay, now in simple terms it means that if the length is above 740, then the farmer should not cultivate. Please, in this I'm a bit okay, I want to be a bit clear here is that when you have high atmospheric pressure, it cannot favor crop growth. High atmospheric pressure cannot favor crop growth, and it's very bad. So okay, therefore if the length is 740 millimeters, then the farmers should not cultivate land. I know someone is wondering, why are we just calling it 740, yet in the question 740 millimeters, yet the question had that word millimeters and Hg. This one means mercury. So if you have measured 740 length of mercury, you can just leave it like that. That's what you're meaning. Okay, the farmers should not cultivate if it is above. However, if it is below 740 millimeters, they should cultivate. If it is below or equal to 740, they should cultivate. If it is above, they should not really cultivate. All right, good. So what you're meaning by the length is simply this. You measure and realize that this length maybe is now equal to 740. The distance from here up just right there. If it's equal to 740, then they can go and cultivate right there. That gets part A of our question answered. Let's then look into another part. Without fear, let's go there. Okay, great. Let's look at this. They're saying part B, explain how clean water is obtained using the kettle, pot, and metal sheet. Now remember, these people here were advised that they had a problem of clean water, so they needed to get some clean water, but this was the advice the government gave them was, so the government has advised the region to make kettles, you see that, and pots using clay. Oh, okay. Use them with metal sheets, okay, to address the issue of clean water for drinking. Now take note of that word, clean water for drinking. Now again we come back in this scenario here ahead. Look at this. That word drinking, the thing, the amount of heat required to vaporize 2 kilograms of water. Do you see that? For drinking. So it means that in order for these people who have been given a pot, is it okay? A pot. Okay, a pot. So you realize that for them they are boiling water for drinking. So it means that, and here the question is telling that the amount of heat. So it means that for them to obtain pure water, given the clay pot and given the kettle made out of clay, they should heat the water such that they can obtain clean water. How can they do that? Of course, think about what you call what? Evaporation. Why? They are saying they are saying that, okay, to vaporize, you see, to vaporize. It means that we think about evaporation and the condensation or cooling of the vapor. In simple terms, we'll get this covered. Let's go there and have this done. Okay, I hope that breakdown I've given you can at least put you on board together with me such that we can move together in this scenario. Okay, quickly, without wasting time, let's get the diagram drawn. That is our kettle. That is our kettle straight away. I'm trying to draw our kettle. Okay, hope it is a nice one, by the way. Alright. We get done with our kettle. That is our kile. Our kettle made out of kile. That is our stand, or you can call it a support. Okay, we are getting it done. That is our kettle in simple terms. So we're going to heat the water. We're going to heat the water. Yes, we're going to heat the water, by the way. This is the heat. You can see it from right there. This is heat. Now this is our pot. We're getting our pot ready. Hope it is a nice one also. Okay, good. Now this is our metal sheet with a hand. Of course, so that doesn't burn you, we have a hand right there. So we are putting in the water which we are heating. Of course, guess what? As you are heating the water, this water is going to evaporate somewhere. So that is our water. Just look at how cool that is. Alright. Now, okay, let's move on. So you're putting in our water. Quickly, we get there with our water. So we're getting our water ready. We have our pot there. Now, this line you're seeing here, I'm taking it to be our ground, such that these things can all lay on the ground very well. It's very wrong to draw like that diagram. We have a stand right here, then you have the pot just hanging in the air. That can't really work out. Alright, so let's get there. Okay, now look at the time we have been heating our water, and look at this. The water started vaporizing. Like we are, the water is hot now and is vaporizing. Just see how cool that is. How water is vaporizing. Now, for us, what we want is to have the vapor move out like this. Heat here, cool, then the droplets will come one by one downwards. Look how cool that is. Okay, good. So next, they must follow this route here. The water is vaporizing indeed, really boiling, too much heat, very intense heat. The boiling is too much. You see now our vapor is going up, again comes here, and again comes, hits here, and again hits there. Very good. The dots must come in. Okay, oh, lucky we are. We have a dot already coming in, another dot down, another dot, and another one. Then water starts coming in. Of course, water starts accumulating slowly, like that. Every time the water accumulates, this is our water right there. Okay, yes, you can see that water there. It's a bit cool, I guess. Now, so this is our water right there. Now, what must you know about this? So it means that here, this is now evaporation process. Look into that. Then at this point here, we have what we call a condensation process. That is simply condensation process. Okay, now I told this is a metal sheet, and we shall get this named. Let's get this named. Alright, so that is our kile pot, just to remind you, and that is simply our distilled water after heat, the water which has cooled from water vapor, and that is simply our water from the condensed water. Yeah, from the vapor we have formed that droplet. Of course there are very many, but we name one at a time. This one here is our metal sheet. Right, that is simply steam from the boiling water. So the gaseous stuff which comes out of water which is boiling, we simply call it steam. So next, this one is impure water. The impure water, maybe it can be dirty water. Okay, think about the water which is very dirty. Think about when it has rained. that running water maybe that's what these people are facing here. You can get it boiled and get it clean just in this way, just using evaporation. Are you seeing that you can get clean water out of this? Now I know this sounds funny and a bit crazy to you, but lucky you are that you're in areas which have enough of the water. But in some areas, this is the way to go, or the order of the day. Okay, so this one is our kettle. This is the steam coming up there. This is the metal sheet. This is the handle where to hold it from. The water from condensed water, the clay pot like there. Distilled water, the water which has cooled from this vapor, come like this, cool and comes down. It has accumulated. Just know with time it will go up, and maybe they can fill up a pot in the long run. I think how this is a control measure. You can try this out any day, anytime. Of course, I know with time you'll be able to also move places, far ends, places in other countries, and maybe you'll find that this will be the order of the day. Let's go and get this into descriptions and we see. So let's go there. All right, great. So we are now saying that the impure water is poured into a kettle. Yeah, we have everything in the diagram. Say the impure water is poured into the kettle and then is heated to boiling, producing steam. Steam is what you call vapor in simple terms. Okay, the steam is directed through the kettle spout. Okay, a kettle spout is this. Let's go and look into this. A kettle spout is this. A kettle spout is this. A kettle spout is this here. This is a kettle spout where the gas comes out from. You call that a kettle spout. Okay, let's get here back again. So through a kettle spout onto an inclined metal sheet next to the mouth of the clay pot. Yep, there we are. So the metal sheet absorbs the heat from the steam, causing the steam to condense. This word condense may also mean to cool. Cool into pure water droplets. What happens next? These droplets fall into the clay pot, collecting distilled water safe for drinking, while impurities remain in the kettle. Okay, so in simple terms, that's what you're getting here, that we get the impure water boiling, come out in terms of vapor. This vapor follows its way up via the spout. Of course, we have an inclined metal sheet here. The water will be instead in that metal sheet. The metal sheet will make the vapor to cool to form droplets, which droplets will come downwards, making the water to accumulate in simple terms. That gets part B, Roman number 1, answered successfully. Let's still continue straight away. So we resolve this. Hope this is really making some bit of sense. Okay, here we are, another thing. Roman number 2, explain how the banana fiber cooled the houses. Okay, of course here, those people who grew up in the village, we have you covered right here. You got some big stories to tell about these banana fibers. I know people have grown specifically 100% in town cannot even know what a banana fiber is. Okay, now it all begins with this story here. Now, about banana fibers, we must be knowing this. What do banana fibers do? There are 4 good importances of a banana fiber in the house. Now, these people here, the government advised them that they should put banana fibers on the walls. Okay, imagine on your hanger where you put the clothes and it is just full of banana fibers. Banana fibers, we have them right here. These are the banana fibers you're talking about. Get this, put it up on your hanger, or yeah, put it around the house as a way to reduce on the too much heat in simple terms. So first, the banana fibers help in what we call thermal insulation. Okay, look at this word insulation. It means that the banana fiber insulation helps to reduce heat transfer between the exterior and the interior of the building, keeping it cooler, meaning that these banana fibers can absorb heat from them. Remember, heat, this is like this, this is like this. Now, if this is hot and this is cold, I want to explain this. This is cold. Heat moves from hot to cold. That's how heat moves. So, since the room is hot and these banana fibers are cold, moreover watery, so the heat will be absorbed by the banana fibers. That explains why after some time those banana fibers will just dry up. Don't know whether that carries some sense. Next, it is eco-friendly. Banana fibers are sustainable, renewable resources, making them unattractive like After they've cut down a banana plant and have removed the bunch of matoke or bunch of banana bunch, so what they remain is can be of great use. So it is eco-friendly, meaning that, of course, what we call wastes can be of great importance as far as reducing heat is concerned. That's what we're meaning by eco-friendly. The next year they're saying breathability. The fibers allow airflow, promoting natural ventilation. Yeah, they allow airflow. They are a bit aerated. Okay, good. So using banana fibers in construction can contribute to energy efficiency, reduced cooling costs. Yeah, of course, when you're using this is an advantage that you use banana fibers other than, of course, these people, you can afford a fan. Of course, the people in the AI generation, they know a fan. For us back in the days, we got to know of a banana fiber. Or, you ever seen, especially on unipots? Unipots are in this shape here. They are always most times in the police posts. You find when on any unipot which is metallic, they plant some flowers on top. That is also one way of making it a bit cool, because just not they are always hot during the day and also very cold during 90 hours. Alright, so with that, let's go and get the description into details. Alright, we get there. So realize that. You realize that. I'll get this. Okay, good. So the saying, water molecules from the banana fibers, yeah, of course, the water is there, absorb latent heat from hot air. Yeah, so for you, just look at heat. And the word latent may not be of great sense, maybe, but the word latent means hidden, absorbs the hidden heat. You can't see the heat. You can't. There's a heat which can be around the house, but you can't even feel it. Okay, latent heat from hot air in the room. Yeah, the water molecules absorb the heat. Okay, water molecules with high kinetic energy overcome intermolecular forces and escape from the liquid surface into the air as vapor. Like as the heat from the surrounding is heating the banana fiber, which is containing water, simply here the water will evaporate. But the kind of evaporation here will be that it will be some cool breeze which will come out of the banana fibers. Okay, some good smell also, I guess. Okay, as heat energy is absorbed, the temperature of the air and the nearby surfaces decreases. Yeah, the temperature reduces, of course. The heat is being taken in to make the water become a vapor. So there the temperature will cool down, causing a cooling effect in the room. So that still again gets our part C, Roman number. Part B, Roman number 2, successfully answered. So without wasting time, let's go and look into part C, if it is there anyway. Okay, if it's there anyway. Okay, part C, like we have it right here. Okay, the saying part C, determine the specific latent heat of vaporization of water. Determine the specific latent heat of evaporation of water. Now, the specific latent heat of evaporation of water should come from, look at this, we have the amount of heat required to vaporize 2 grams of water. Not that the mass, okay, it means that the mass is of 2 kilograms. You see that? Now the temperature here is 60 degrees, but what you should know is that we have theta 1 and we have theta 2. Theta 1 is the temperature at start, which is 60 degrees right there, Celsius. Now theta 2, since we are boiling, as a substance is vaporizing, just know it is already doing what? Boiling. Now we know maybe this one is pure water, and pure water boils at 100 degrees Celsius. Hope you can look into that. Okay, good. Now the amount of heat. Now the word amount of heat, we always use letter Q. Amount of heat same as quantity of heat, letter Q. So the amount of heat is 4.55. You look into that. 4.55 times 10 power 60 joules. That's the quantity of heat required right here. Meanwhile, don't forget, we are using water. Water has got what we call a specific heat capacity. We have it right here. Specific heat capacity of water is that. Now specific capacity of water, comma, we use letter C, is 4,200. Okay. Specific capacity of water. For those who covered heat, I guess you know some of the terminologies I'm using here. Alright, good. So, however, if you don't know what any of these terminologies mean, you can hit my inbox on WhatsApp and I will be there to respond. Now, what you should know is that the quantity of heat will be equal to, first of all, before this water be boils, the mass of water we have with a certain specific capacity must move must undergo some temperature changes, like okay, theta 2 minus theta 1. For it to become hot from 60 to 100 degrees, there is some heat there. The change in temperature brings the some quantum of heat there, plus now to find the latent heat vaporization should be the mass times the latent heat of vaporization itself. So this is the formula we're going to use. We have the Q, we have the M, we have the C, we have theta 2, we have theta 1, we have the mass, we want L of V. We get it straight away. Let's go there. Let's get there. Without wasting time, let's get there. Right. Okay, part C, I think here we are. Okay, let's get there. Okay, now we are getting it summarized that the amount of heat Q required to vaporize 2 kilograms of water for drinking from 60 degrees is given by, so Q, this is the formula we use, M L of V, whereby M is the mass, L of V is the latent heat of vaporization, M is the mass of water, specific capacity, the boiling temperature, which is 100, theta 1, which is 60 degrees. We're getting there. We're clear. Okay, so where M is equal to that, we have everything summarized for you. So the mass is 2 kg, we have it from the summary, that is our specific heat capacity. We have our theta 1 is that. Now this theta 2 is 100. They have not given it to you, but you should know that boiling point of water is, as it turns into vapor, is always at 100 degrees Celsius. But here not just water, but pure water. Anyway, we are taking an assumption, I think. Okay, great. Doing that, we shall have to proceed straight away without wasting time. Let's get this covered right away. So we go. So we now substituting. Okay, now the quantity of heat Q is 4.55 exponent 6 joules. Oh, sorry, this is not joules per Kelvin, it's meant to be joules straight away. All right, so here we are. Next, let's look into this. So we have the quantity of heat is the 4.55 exponent 6 joules right there. So from the formula we know that, from this formula here, I want to substitute in meters of this. So we have this right here in the formula equals to, we have the 2, which is the mass right here. We have the LOV maintained there, which they want. We have the mass again, which is 2. We have the specific capacity, which is 400. We have the theta 2, which is 100. We have the theta 1, which is 60 degrees. Those are the substitutions. Next we see, realize I shall have 4.55 exponent 6 equals to 2 LOV plus, when you multiply this, you will get 336,000 right there. So the next step, let's go and see how we can get LOV. So the next step is start off without wasting time. So 2 LOV is equal to 306,000 minus 4.55 exponent 6. I want to explain this right here. That, okay, erase that off. Okay, look, when we happen to take this side, then we leave to LOV the subject. Okay, after that will become a negative, then we proceed. So we are subtracting. That now give us okay, so we shall now say divide by 2. Okay, I don't know whether this is really okay. Alright, great. So we have harmonized it already. So this will be now 2 LOV is equal to 4.55 times 10 power 6 minus that. So we get this harmonized. We say we are dividing by 2 on both sides. That when we subtract this minus that and then divide by 2, this will cancel to give us LOV. So the final answer you'll have right there will be LOV will be equal to 2.107 exponent 6 joules per Kelvin, joules per kilogram. That is the specific heat capacity, rather than latent heat of vaporization. And that gets our part C of this question fully and successfully answered. Okay, let's move on to another part. Let's move on to another part without wasting time. All right, good. So now with that we have finished part C. Let's now go to part D. So part D says Part D says, okay, part Roman number 1, find the height to which the tank must be raised to supply water at the required pressure. Which height must we raise this tank to? Let's go and look for this in the details here. Okay, now first of all, it begins with this story here. They're saying the total pressure sufficient for the taps and irrigation is this. Now if you have the pressure is equal to 15 kilopascals, so it means that we can get this 15 pascals to just the pascals. So we have multiplied by 1000, so times 1000. The answer we shall get there will be in pascals. Why 1000? To remove this kilo here. The word kilo means 1000. So having done that, the G, acceleration due to gravity G, is 10 meters per second squared. I guess they have quoted it for you here. Okay. I can't really see it here, but they meant to quote it for us. But you all know that G is that. Then next, we need the height. Remember, we want to know the height. From the question, they're saying that, in fact, they want to know the height to which they must put the tank in order the pressure to be sufficient. And the pressure is that. So, we have the pressure right here. We have the G is right there. Now, the density. The density, this one here is density. Density, the symbol of density is rho. The symbol for density is like that, rho, more like letter P. So, the density of water, you all know that is 1000 kilogram per meters cubed. No need to ask, this is already there. Now, we know that pressure in liquids is equal to height times density times acceleration due to gravity. But the pressure is 15,000 equals to the height h times the density, which is 1000, times the acceleration due to gravity, which is g. Okay, like that. So here we shall need to get the value of h. The value of h we shall get here will be our final answer, or the height to which they must place the tanker. Let's go there straight away. Let's go there straight away. All right, good. Let's go there straight away. So without wasting time, let's say pressure is equal to that, we know. So where P is equal to that, but then we are getting it converted. I explained that. Then in the next step we shall say, okay, so we have the pressure is 15,000 pascals, the density of water is 1000, then the acceleration due to gravity is 10 meters per second squared. Then of course we get it from the formula that pressure is equal to P is equal to that. So find that this is our pressure here, this is our density, this is our G, and this is our H, which we need the height. So the algebra says we have it in that format. Then dividing both sides by 1000, shall now have our H as 1.5 meters. Now why are we writing the answer in meters? An explanation. Look here, even the acceleration due to gravity is in meters. You see that? Here it is in meters cubed. Do you see that? So that's why we are writing our answer in meters, not in millimeters of mercury or anything. Okay. Then we move on. Then also even the pressure has been given in pascals, not in millimeters of mercury. That's what we are trying to bring out here right away. And now that gets part A, or this part also successfully answered. We've got part D, Roman number 2, straight away. Now part Roman number 2, what do they want? Let's go there. We're about to finish. Let's go there. Okay, good. So you realize that we're now going there. Okay, so let's now go and see the part D, Roman number 2. We can look into it. Okay, here we are. So part Roman number 2, allow me to resolve this. Alright, good. So part Roman number 2, they're saying, describe how water is ably pumped to the elevated storage tank. Now pumping water, what are they using? That's the first thing you must ask yourself. Let's go there and see what are they using to pump this water here. Let's go right there. Okay, good. So they're saying that, okay, they're saying that we have from around here. Okay, so they're like, we can start from here. Build the high water tanks out of repurposed plastic containers locally made to act as water reservoirs. Okay, the population has been advised to extract groundwater. Are you seeing that? Using a handy pumps to raise the water into the tank, so to bring water to the residences. The major word here is a handy pump. So in simple terms, I'm going to describe how a handy pump works, how a handy pump simply works right away. So we're going to see how a hand pump simply works. Okay, before we go into that, let's go pictorial a little bit. Let's go pictorial. Now, this is a picture of what you call a hand pump. This is a picture of what you call a hand pump. Yes. Now, a hand pump in here, we have what you call a piston. We have a cylinder. I don't want to go deep into that. Piston rod. We have the force rod. This is where you apply the force. Then the water outlet, or sometimes they call it a spout. Then a water suction line. This is where the water climbs, water goes up there. Now, a hand pump is just like a borehole, just like you can see that this is the water underground, this is the ground level, this is our ground in simple terms. Now, that's how it looks like, but the science begins with this. Let's go there. So the science now begins here. Oh, I don't know whether my fine art is a bit okay, but I tried to take time and draw this. I don't know whether it would make some sense, because I looked for some good designs, but I couldn't really get one which can suit the explanation of this. Now, in here, these 4 pictures will be enough for you to understand how a hand pump works. A hand pump, think about a borehole, of course. Now, as the story begins, here we have water from underground. This underground water. Now, just note, as that water is there, there is always atmospheric pressure applying on this water here. Atmospheric pressure applying here. In a way that this water here, in the case we create any space here where this air would be, if in the case we create any space here, this water will just come to occupy that space there. This water is under pressure. Water is under pressure. That's what we mean here. Now, what happens is we have what we call the valves. We have what we call the valves. Now, this one here is valve A, and this one here is valve B. These valves here are moving. They are flappy. Flappy are meaning they are bit shaking. Like, so for example, what I mean by flappy is if you put a rule on a desk and leave one end in the air, then you rotate it. That movement there is what you mean by flappy, meaning that this one this one here can open and close. Even this can open and close. Now, there is what we call upstroke and downstroke in this. Now, upstroke means what? Upstroke, we don't really look at how your hand moves. Like, if you're in a borehole, then you push the hand downwards. That's what we call upstroke. And if you're in a borehole, then you push your hand upwards. That's what we call downstroke. It's a bit contrary, but a stroke, we look at it in what happens to this piston in here. This piston, once the piston goes up, that is upstroke. Once the piston goes down, that's downstroke. So realize that as for you are pushing down, the piston is coming up, so we call it upstroke. As for you are pushing up, then the piston goes down, we call it downstroke. Hope we are clear right there. And guess what? Just these 2 steps are enough to get this described. Now remember, there is too much atmospheric pressure acting on this water. Too much atmospheric pressure acting on this water in a way that any space in this tube here, the water will just go upwards like that. Now we go to the downstroke. Downstroke, you push the hand down. When you push the hand down, the piston will move up together with the valve. But as you're going up, the air which is coming downwards like this will make this valve to be closed like that. I hope you really see that. As this one is okay. As we are going up, just know this one is going up. Now the air will make this valve to be closed. As this one is going up. Now as that one is going up in the upstroke, remember we have created some space here. Some space. Remember, the water within here was being acted upon by atmospheric pressure, and this water was only waiting for a chance. Any space here, it comes and occupies. So when the water, once the piston moves up together with the valve A closed, the space in here, the water will rush in to close. Now the water will push this valve B, which is down here, and to make it open, so the water will move and enter into this region here like this. That is in the upstroke, like that. Now next we go to the downstroke. Remember, we had our water already up in the chamber. So as in the downstroke, meaning that for you are pushing up, So this piston is coming down. So as it's coming down, look at this. As it's coming down, let's look at this. As it's coming down, the water will be forced to pass through this. Okay, as it's coming down, the water will climb to pass through this. So mean that they will make this valve to open. Meanwhile, as the remember this one is coming down. This whole stuff is coming downwards. It's coming down like this. This whole part is coming down. So it means that the water will find its way out to escape. Its way out to escape. So we'll make this valve to open. But as it's coming down, as this one is coming down, I'm explaining this step. As it's coming down like this, some water will push this valve here to close. And that's what I have right here. So that valve is closed. So this one comes up to the brim, to the bottom. Now guess what? As we go up, this valve which is open will close. So as we are going up, this valve which was open will close. Why is it closing? It's because as we go up, the water particles, allow me raise up this. The water particles will push this valve like this to come and cover up this area, and that's what I have right here. Then as you're moving up, remember there is some water also forcing itself up, which will make this valve to open, and we have it right here, there. Now remember, this valve which closed had some water trapped in this area, and they moved up with it, which will move out of the spout, and hence the water will be delivered to the residents. Maybe from this spout here, I can get some bit of connection. Maybe from here we put a pipe, we put our pipe here like this. Our pipe, okay, just assume it is a pipe. Then onto our tank which we will have put somewhere made out of the repurposed plastics, and then the residents will be able to get the water in simple terms. Okay, that is done. Let's now go and see the real details right away. Let's step into this. The real details, here we go. Okay, now in simple terms, we get this described as saying the piston of the hand pump is pulled upwards. So I was telling you the piston is this. This stuff here is the piston. Okay. This part here is the piston. Allow me clarify on this. This part here is the piston. This one here is the piston. Okay. So they're explaining this upstroke first of all. So okay, let's go there. Alright, good. So we are saying the piston of the hand pump is pulled upwards. The volume inside the pump cylinder increases. Like we had it right, like this. Like this. We had some valve right here and the water underground. So when they pull the piston upwards, okay, when they pull the piston upwards, what will happen? The volume also will increase, meaning the volume is more like the space. The space will increase. Of course, there will be some space created, and there water will come in. So, hence creating a partial vacuum inside the pipe of the pump. Here they're explaining upstroke. Okay, atmospheric pressure, the pump pushes downwards on the surface of the groundwater. So, atmospheric pressure pushes downwards on the groundwater. Now what happens? Because the pressure inside the pump's pipe is lower than the atmospheric pressure. Now what they're meaning is that the atmospheric pressure is always greater than the one in the pump. So the pipe, it means that now the water will just climb upwards in simple terms. That's what I'm meaning here. Okay, good. That is saying, okay, the higher external pressure forces water up into the pipe and then out through the spout. Yeah, I've explained that. When the piston is pushed down, this water is then pushed into the elevated storage tank, which acts as a reservoir. Okay, in simple terms, that's how we get that described. You can relate this description with the pictures I've given you, then it can carry a little bit of sense. Or you compare with your notes still, no worries. We now go to part D, Roman number 3, and we have this chapter also successfully closed. Let's go there. Now as you're going there, please, I know there's some people who send me papers. Please just know it requires enough time to get this ready. So if you send multiple papers, just know that in a day I receive over 10 papers from different people, and I can't get them handled right here. So I always pick out the most sensible ones, more like this Jjeb we are dealing with. Okay, Roman number 3, here we go. What long-term solutions to these problems do you recommend these people to adopt? So the problems were too much heat. The problems were water scarcity. The problems were In fact, a lot. That too much heat. Can't we even utilize it in another way? Water scarcity, too much heat in the house. Let's go and see the solutions we can provide these problems in simple terms. Let's go there and see the way forward. Let's go there and see the way forward. Okay, quickly, here we are. So these solutions are just simple. See, we can say by planting trees. Yeah. Okay, by planting trees to reduce heat waves that reduce urban heat island effects and so improving air quality. If you're a student, you can just say planting trees to reduce heat waves. That is all. Some of the terminologies here may not carry sense. Okay, or even going about to cram them may be a bit hectic. So installing solar powered pumps for drawing water. Yeah, other than a hand pump, which is very tiresome, more like the boreholes we have, they can bring solar powered pumps. Yet since we have too much sunshine there, the area is too hot, too much sunshine, so you get a solar, and then that sunshine which disturbs you, which is even a nuisance to you, become useful in a way that it gets you some water. This utilizes renewable energy, reducing dependence on fossils while ensuring water access for storage and community use. You have explained that the sun, which is a nuisance to us, you can charge the solar batteries and make the machines run to get for us water. Constructing houses with ceiling boards and clay tile roofs. Yeah, you have seen those clay tile roofs, the tiles. Yeah, that can really prevent, or ceilings, of course. Now this improves the thermal insulation in your homes, reducing indoor temperatures, enhancing comfort during the heat waves. Okay, this is a bit self-explanatory. Then also installing water purification system to help treat water for drinking. This is a bit expensive, not all that cheap, but since you're dealing with the community, you never know they can contribute. So installing the water purification system to help treat water for drinking. Okay, to reducing the risk of waterborne diseases and improving public health in the communities. So yeah, the answer you give must be well elaborative and explained. You must explain the point, the remedy, tell us the solution, and then which remedy are we solving, what are we preventing in the long run. Okay, simply we are ending there, and this marks the end of item 5. More to come, item 6. Thank you.